In this lecture, we will be covering the topic of lines in R3, or three-dimensional real space. We're going to think about a line that goes through the point P0 and is parallel to the non-zero vector V. So if we imagine what our point looks like in space, so suppose this is our P0, and then we have our vector V, to which our line is parallel. These two things together will define a line. So specifically, we're going to have the line depicted here. So having a non-zero vector parallel to the line and a point on the line identifies the line uniquely. Now, of course, you can use any vector parallel to this V, so it could be longer or shorter or pointing in the opposite direction, and any point on the line. But one point on the line and a vector parallel to the line are sufficient to identify the line. Now, in order to understand how we mathematically define a line in terms of equations, we have to move away from the way we think of things in the xy plane. When you think about your line as a linear function, y is a linear function of x, that's not going to work in R3, in the x, y, z space, and that's because linear functions of x, y, and z, as we will see in a subsequent lecture, define planes in R3. So we need to do something a little bit different for lines. And we can see how that works by working with this picture here. So first, we need to get some variables involved. And so let's define a generic point, say P, as just the point x, y, z. And we want to characterize what it means for this point P to be on this line. So suppose that P is here. So again, this is the point x, y, z. And so we will have coordinates x, y, and then z up here on this axis. And we can label our P0. We have x0, y0. The first thing we note is that for this P, this generic point P, with coordinates x, y, z, to be on the line, if we were to form the vector P0P, we can see that this vector has to be parallel to V. So this will be a key insight. For that P to be on the line, if P0P and V are parallel, that means that one is some scalar multiple, say t, times the other. So mathematically, this is what it means for P0P and V to be parallel. So this will be a key insight for us. And we can say for some scalar t in the real numbers. Well, let's set up some more infrastructure. So first, let's set up some position vectors. So let's set up a position vector for P0. So that's going to be the vector pointing from the origin to the point P0. And we're going to call that R naught. So R naught is the position vector for the point P naught. And then we'll do something similar. We'll call R the position vector for P. And so when we draw this position vector, we get something like this. Now that we have these two vectors depicted, let's write them down. So we know R naught as the position vector for the point x naught, y naught. Z naught would be the vector x naught, y naught, z naught. And then in a similar fashion, R, being the position vector for the point x, y, z, is the vector x, y, z. And we now can come back to this idea of having built the vector P naught P. And so that vector P naught P, we know that we form this vector by taking the coordinates of the end point and subtracting from them the coordinates of the beginning point. So we have x minus x naught, y minus y naught, z minus z naught. But notice that this vector is nothing more than the difference between the vectors r and r naught. Now, bringing things together, P0P, we noted at the very beginning that that had to be T times V because P0P and V were parallel. So we now have T times V has to be equal to P0P, which we just set up as R minus R naught. And this will give us the key vector equation, or a vector equation, for this line. So summing up what we have on the previous slide, we have that this P0P, as we constructed it here, was equal to R minus R0, was equal to TV, and now we focus on this equation. And that is the definition of a vector equation of the line through the point P naught and parallel to the non-zero vector V. We write it this way. Everything in this definition is defined exactly as we had defined in that previous picture. And so you can look at this and think of something similar to what you've done in calculus. Remember that R is the position vector of the arbitrary point on the line. R naught is the position vector of your point on the line. And V is the vector parallel to the line. T is the parameter. So this looks similar to variable equals slope times the parameter plus an intercept. This should make you think of y equals mx plus b. So this is very similar in spirit to what we've already learned for what we would call the point slope formula for a line in the xy plane. More often, we actually work with the components of this equation, and we do that in the following way. Let's just take this vector equation 1 and write down what it means. R is xyz. We have t. V, the vector v, is the vector abc, and r naught is the vector x naught, y naught, z naught. Now, for this equality to hold, we need equality to hold in the components. So we need, say, the equality to hold where x equals at plus x naught. We have that equation here. And we would say the same thing for the y components. Y equals b times t plus y naught. And z equals c times t plus z naught. And with these component equations, we define them as the parametric equations of a line. So parametric equations of the line through the point x naught, y naught, z naught, and parallel to the non-zero vector v equals abc are given by these equations that we just derived. It's important to note that parametric equations for a line are not unique. And that happens because any point on the line and any vector parallel to the line will give you parametric equations for that line. And if you think about parametric equations more generally, for say a parametric curve in space, a parametric line certainly qualifies as a curve. So if we have a line in space, we can think of this set of parametric equations or the vector equation as one possible parametrization of the line. And let's think of it as the parameter t being time. And if you think about time running it, say, both forward and backwards, so say you start at 0, for this parametrization, at the point p naught, this is where you are at time 0. And if you start to run the clock in the positive direction, think of this as a particle, it will move along the line in the direction of v. If you run the clock in the negative direction, it will move along the line in the opposite direction of v. Different parametrizations come through different sets of parametric equations. So you could imagine you would have a set of parametric equations for every possible way to parametrize a particle moving in time along this line. So in that sense, parametric equations are not unique. And so this means when you're working on problems to find parametric equations for a line, if you look at a solution and yours doesn't match, it doesn't mean that you're wrong. It may just mean that you have a different parametrization of the line. In such a case, you can check points. Any 2 points will define a line. So if you get an answer and 2 points are on your line and 2 points are on the other parametrization that you see that's given as the correct answer, if the same 2 points are on each parametrization of the line, then you know you've done it correctly. Let's do an example. So let's find parametric equations of the line through these 2 points. P naught is 1, 2, 0, and P1 is 0, 4, 2. So P naught, we would have 1, 2, 0. So P naught is here in the xy plane. And then P1 is the point 0, 4, 2. So P1 is here in the zy plane. And the line we are interested in passes through these 2 points. So, going back to our derivation, we need 2 things. We need a vector v parallel to the line, and a point on the line. But of course, we already have a point on the line. In fact, we have 2 points on the line. So what we really need here is the v. And we can see that a natural way to do this, like in our derivation, is to form this vector P0P. And we know that P0P is parallel to the line. So that will be our v. And I should point here, we need this. We're not given this v. We need it, so we have to construct it. So P0P, recall the way to do this is you take the coordinates of the ending point and subtract the coordinates of the beginning point. So we have 0 minus 1, 4 minus 2, and 2 minus 0, which is minus 1, 2, 2. So our vector P0P, really we should call it P0P1. P0P1 is minus 1, 2, 2, and we know that that is parallel to our line. And so this will play the role of A, B, C. So we know the parametric equations for our line. We have x equals AT plus x naught, y equals BT plus y naught, and z equals CT plus z naught. We have our ABC from our vector v here. So we have minus 1, 2, and 2, each of these multiplied by t. And then we pick any point on the line, and so either of these will do. So why don't we use P naught, and we have 1, 2, 0. And this gives us parametric equations for our line. Note that we could have used P1, and we could have had 0, 4, 2 here. And again, those would just be different ways to parameterize the line. And if you think of the parameter t as a clock, the way we have it, when t equals 0, our x-coordinates are 1, 2, 0. So we would start here at time 0. In the other version, if we used P1, at time 0 we would be here at P1. But either way, these two alternative parameterizations trace out the line. So these would be our set of parametric equations for our line. Now, in the special case where all the components of our v are non-zero, we can actually solve for the parameter. So let's solve for t in this case. And so in the x equation, we would get t equals x minus 1. In the y equation, we would have y minus 2 is minus 2t. And if we divide by minus 2, we have t equals y minus 2 over negative 2, or 2 minus y all over 2. And for the z equation, we would have t equals minus 1/2 z. And what you can now do, because you have t solved for in each of these cases, is we can just write these as equal to one another. So we can say x minus 1 is 2 minus y over 2, is minus 1/2 z. And this is what we call symmetric equations for the line. And so this is often something we are asked to do if possible, and it's only possible if you have all the components of the parallel vector v being non-zero. So this is another way to write the line, and essentially this is saying because you can solve for the parameter t, you don't need it. You don't need to write it down. You can just say these things here are all equal to the parameter, and this captures the parameterization of the line. We will look at more detail about lines in space. In particular, in the next lecture, we have to talk about what it means for the relationship, the possible relationship between two lines. And when you're in the xy plane, you have two possibilities. You have two lines either intersect or they don't. And in the case when they don't, they're parallel. But we have one other case that we have to deal with when we look at lines in space, and that will be explored in the next lecture.